In this video, we'll be talking about rotational work and power. So, what's the formula for work? Well, the formula for work is a dot product, but assuming that the force and the distance displacement vectors point in the same direction, then you will omit the cosine value in their dot product. So, what is the force equivalent in rotation? Well, the rotational equivalent of force is tau, and the rotational equivalent of distance is radians. So all you need to do is replace force with tau and distance with radians. So work is equal to torque times radians. Now, the unit for work is still joules, so it's some measurement of energy. And work is still your change in kinetic energy per the work energy theorem. So even in rotation, these rules still apply. But if you want a real derivation of this, then we will show you the actual formulas that form this equation rather than doing the equivalences. So, not work, force times radius is equal to torque, assuming that the force and the radius form a 90-degree angle with each other. But if you're taking a high school or algebra-based physics course, then you're likely going to just worry about this. So torque is equal to force times radius. If you were to isolate force, then you would get that the force is equal to the torque over radius. Now, how about distance? Well, displacement or distance is equal to radians times the radius, and you will get the distance. So if you want to isolate distance, it's already isolated in this problem. So let's substitute in our values for force and displacement. So we'll substitute our values for force and for displacement here. So the force substitute is torque and radius. And the substitute for distance is theta and radius. So capital R, I guess, for radius. Same as lowercase r. I should have stayed consistent with that. But what happens is basically that this cancels out. And work is equal to torque times your radial displacement. Okay, how about for power? Well, in the previous problem, we determined that work is equal to torque times your radial displacement. So what is power? Well, power is work over time. And that's equal to power. And rotational power is also equal to, well, rotational work over time. So if we write down tau, so this is work over time, this should equal power. But what does radial displacement over time equal? Well, radial displacement over time equals angular velocity. Therefore, power is equal to torque times angular velocity. So now that we know these things, let's go into some problems and use what we know. So for this problem, you have a wind turbine that rotates at 20 revolutions per minute. And its power output is 2 megawatts, so 2 million watts. What is the torque produced on the turbine from the wind? Well, let's find your angular velocity first. Your angular velocity in this case is equal to 20 revolutions per minute. But in order to use angular velocity, you need to turn this into radians per second. So we need to do some unit conversion. 1 revolution is equal to 2 pi radians. And 1 minute is equal to 60 seconds. So all we need to do is multiply 20 by 2 pi divided by 60. If you do that, then your angular velocity is 2.09 radians per second. Well, the reason why we calculated angular velocity is because we're trying to solve for the torque produced by the turbine from the wind. But remember that the formula for power is torque times angular velocity. So using angular velocity and using our power already given in the problem, we can solve for the torque. So when we isolate torque, you get power over angular velocity is equal to torque. So if you write down 2 million watts of power divided by your angular velocity, 2.09 radians per second, you should get a final power of 95,000, sorry, a final torque of 95,600 and, oops, not 95,000, 956,000 and 938. There you go. Newton meters. So Newton meters is the unit for torque. So for this problem, we need to solve for the power being provided to the propeller 3 seconds after it starts rotating. So the formula for power is torque times your angular velocity. So we're given an angular velocity, at least the final angular velocity, after 6 seconds. So we don't have the angular velocity we need after 3 seconds. But we have an angular velocity of 1,000 revolutions per minute. So we need to do some unit conversion. 1 revolution is equal to 2 pi radians, and 1 minute is equal to 60 seconds. So the minute unit cancels out and the revolution unit cancels out to just leave off radians per second, which is exactly what we want. So 1,000 times 2 pi divided by 60 is equal to 104.72 radians per second, which is quite fast. But this is after 6 seconds of, well, it doesn't state it, but you can assume it's constant acceleration if it doesn't state any otherwise. So if the propeller starts from rest and its final angular velocity is 104.2 radians per second after 6 seconds, but we want the angular velocity after 3 seconds, all we need to do is just divide your final angular velocity by 2, and you will get the angular velocity in half the time. So I need to divide the final angular velocity by 2 in order to get the angular velocity after 3 seconds. So your angular velocity after 3 seconds is 52.36 radians per second. Well, we have the torque in this problem, and we have, so the torque is given, it's 2,000 Newton meters, and we have your angular velocity after 3 seconds, so we need to just multiply these two together. So 2,000 Newton meters times 52.36 radians per second, and what you get is 2,000 times 104,720 watts. So the wind is making a lot of energy. This could run maybe your fridge. I don't know. Okay, I just searched it up. Yeah, it could definitely run your fridge. Your fridge only takes up 300 to 800 watts. If you have a fridge that takes up any more power, you have like $1 million fridge that like has like extra cooling properties or something. But yes, they could definitely run your fridge. I just Google searched it. Okay, let's go on to the next problem. For this problem, we have a uniform cylindrical grindstone that has a mass of 10 kilos. So a mass of 10 kilos and a radius of 12 centimeters, which is equal to 0.12 meters. What is the rotational kinetic energy of the grindstone when it is rotating at 1.5 times 10 to the power of 3 revolutions per minute, which is also 1,500 revolutions per minute? So let's go ahead and calculate rotational kinetic energy. Well, we know that rotational kinetic energy, let's write down part A here actually. We know that rotational kinetic energy is calculated by moment of inertia times angular velocity squared. So let's calculate our angular velocity first. That's the easier one to do. So angular velocity is 1,500 revolutions per minute. But again, we need to do some unit conversion. So 1 revolution is equal to 2 pi radians. And 1 minute is equal to 60 seconds. So the minute unit cancels and the revolution unit cancels to leave off with radians per second. So this is 1500 times 2 pi divided by 60. And then you will get an angular velocity of 157.8 radians per second, which is quite a lot. Okay, let's go ahead and solve for the moment of inertia. Well, the moment of inertia is different per shape, but we have a cylindrical grindstone. So the cylindrical grindstone, so cylindrical shape has a moment of inertia of mass times radius squared. So let's write down our mass. So mass is 10 kilos. 10 kilos, and your radius is 0.12 meters squared, all over 2. So let's put this into a calculator, and then once you put it into a calculator, you should get a moment of inertia of 0.072 kilogram meters squared. So we have our moment of inertia, and we have our radial velocity. Sorry, angular velocity. I keep saying radial. So we can substitute it into the rotational kinetic energy formula, like so. And in the end, so it's 157.08 squared. In the end, you should get a rotational kinetic energy of 888.27 joules. So this is our rotational kinetic energy for part A. Okay, how about this? After the grindstone motor is turned off, a knife blade is pressed against the outer edge of the grindstone with a perpendicular force of 5 newtons. So perpendicular force means that the angle between the two vectors, radius vector and force vector, is 90 degrees. So all we need to worry about is for torque, force times radius. We don't have to worry about the sign value in the cross product. So your force is 5 newtons. The coefficient of kinetic friction between the grindstone and the blade is 0.8. So what we need to do is not use the direct force given in the problem, but we need to calculate the frictional force. So if the grindstone is pressed with a force of 5 newtons, that means the normal force is equal to 5 newtons. If the normal force is equal to 5 newtons, that means your frictional coefficient force is equal to your normal force times your frictional coefficient. Frictional coefficient. There we go. I guess that makes sense. So 5 times 0.8 is equal to 4 newtons. Therefore, your friction force is 4 newtons. And that friction force is what's actually opposing the grindstone's movement. So the friction force is what we're actually going to use in our torque formula. Well, how about the radius? Well, since the knife blade is pressed against the outer edge of the grindstone, that means your radius, or the r vector to calculate your torque, is just equal to the radius of the grindstone. So the radius of the grindstone is simply 0.12 meters. So to calculate the torque, we need to multiply force, 4 newtons, times 0.12 meters. And 4 times 0.12 is 0.48 newton meters. Now that we have the torque, what do? Well, to calculate your work energy theorem, determine how many turns the grindstone makes before it stops, let's write down the formula for work. Usually writing down formulas kind of help us understand what we should do. So the formula for work is torque times radians. So we need to know how many turns the grindstone makes before it stops. Well, how much work do we need to do? Well, the work we need to do should be equivalent to the rotational kinetic energy, since work is equal to change in kinetic energy, and we want the grindstone to come to a complete stop. Your work should be equal to the negative of your current rotational kinetic energy. Therefore, your work should be equal to negative 888.27 joules. But we don't need to worry about the magnitudes or the negatives or anything, as long as we keep them in mind. So the work should be equal to 888.27 joules. Therefore, we can set up this equation with the torque. So 888.27 joules is equal to your torque times distance, or radians. So times radians. And what we have here is just an algebraic equation. We can isolate radians by just dividing 0.48 on either side. So if you divide 0.48 on either side of the equation, then you should get a radial displacement of 1850.56 radians. But this is in radians. This isn't in how many turns a grindstone will make. So we want to turn this into revolutions. So if you have 18, let's make some more space, 1850.56 radians, all we need to do is do some unit conversion. So 2 pi radians is equal to 1 revolution. And in doing this unit conversion, you cancel out the radians unit, and you just leave off the revolutions unit. So what we need to do here is divide 1850.56 by 2 pi. And once you do that, you should get a total of 294.53 revolutions. So, as always, at the end of the video, anytime I use an OpenStax questions, I need to mention them because of the Creative Commons license. Well, OpenStax is an online textbook. I get my problems on there. They're great. If you want more practice problems, go ahead and visit the link down in the description. But if you think what I said today in this video helped, consider subscribing. I would greatly appreciate it. But as always, if you have any questions, put it in the comment section.